Hi, welcome back to AP Chemistry. You are here with Mrs. Mays, and today we're going to work on structural formulas. That is, drawing molecular structures for molecules. So first we need to explore the concept of formal charge. For molecules and polyatomic ions that exceed the octet, there are several different possible structures that we could have. When you have just the octet rule, then it's easy to draw a molecular structure. For certain types of molecules and polyatomic ions, we will have to use the charges on the atoms to decide which structure is best. So let's practice this a little bit. Just fair warning, trying to use the oxidation numbers to put charges on the atoms in molecules doesn't work very well because that's not what formal charge really means. So in formal charge, the first thing that we're going to do is count the valence electrons in the atom, and then we will find the difference between the number of valence electrons on the free atom and those that are assigned to that atom in the molecule. By difference we mean subtracting, right? So we will then count half of the electrons that are in a bond as belonging to the atom. Since it's a covalent bond, that means that atom has to share them, so it only gets to have them about half of the time. So let's use this example in drawing the structure of the sulfate ion. First we'll draw the molecule so that we can get as low a formal charge as possible, and any negative formal charges should be on the most electronegative elements. So that's our goal. Now let's start drawing some structures. Alright, for sulfate ions, first I'm going to count how many valence electrons we have to work with. Sulfur has 6 valence electrons and oxygen has 6 valence electrons, but there are 4 oxygens. And then for the charge of -2, that means we get 2 extra electrons to work with. So that all adds up to 32 electrons that we need to find a home for. So I'll just start off by putting the first atom as my central atom and surrounding it with the remaining atoms, which is, in this case, 4 oxygen atoms. Alright, so how many electrons have we used up here? 2, 4, 6, 8. That means I've got 24 more to go, right? I've used 8. So let's just start putting them around. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Hey, there's a home for every electron, and let's just double check that everything has an octet. Sulfur has 2, 4, 6, 8 electrons. Each oxygen has 2, 4, 6, 8 electrons. Looks good to me. And then this overall structure has a -2 charge, and it seems like that should work out just fine, right? Well, let's check what's called the formal charge. You see, the sulfur, like we said, has 6 valence electrons. So for sulfur, I start with 6 valence electrons, and then we subtract any electrons that are assigned to the sulfur in the molecule. Since sulfur has only bonded electrons, then we know there are 4 pairs, which is 8 electrons, that it gets to have only half of the time. Since they're in bonds, it's sharing them. So if we do 6 minus 8 times 1/2, that is 6 minus 4, we get a formal charge of +2 on my sulfur atom, which is reasonable. It's kind of low, so let's see what the oxygen does. 6 valence electrons for every oxygen, and then each oxygen has only 1 bond, so that is 2 electrons that it gets access to only half of the time. But then there are also lone pairs around each oxygen. There's 1, 2, 3 lone pairs. That makes 6 electrons that oxygen has all to itself all of the time. So 6 minus 2 times 1/2 minus 6 more. That is 6 minus 1, right? 5, minus 6, So that's -1. So every oxygen in this structure has a -1 charge. Now it's not going to be a valid structure if it doesn't add up to have the overall charge of the atom. So let's check our charges. I have 4 negatives and I have a +2. Overall the charge is a -2. So it seems like this ought to work because -2 is indeed the charge of the sulfate ion that it has overall. Seems like that might work. But the thing is, there's a better structure than this for sulfate. Let me show you. Again, I'm going to start with my sulfur in the center of the atom. And this time I'm going to put my 32 electrons arranged in such a way that gives the sulfur more than what the octet rule says it can have. Since the sulfur is in the 3rd energy level or higher, then it has access to D and F electrons. Well, this one has access to D orbitals, and those orbitals are empty, so it can make bonds in those places. If you were in energy level 4, then you'd have access to D or F orbitals, and that gives these certain atoms the ability to go beyond the octet rule. So for the sake of symmetry, I'm going to put double bonds on either side and single bonds on this side, and then let's see what that does for our electrons. So I had 32 electrons available to play with, and I have found a home now for 2, 4, 6, 8, 10, 12 of them. Now I need a home for 20 more electrons. So here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All of my electrons now have a home, and I use the square brackets around the structure to show that the entire structure carries a -2 charge that's extra because we had these 2 extra electrons. So that charge belongs to the whole entire structure. Now let's have a look at what the formal charge says. In this case, sulfur has, again, 6 valence electrons, but now in the bonds we get to have, half of the time, 12 electrons. So 6 minus 6 is equal to 0. Well, that's more favorable for sulfur than having a charge of 2. Remember, we want the lowest possible charge. Let's see, though, what this does for the oxygen. We have some oxygens in single bonds, so I'll call those O sub S, and then I have other oxygens in double bonds. We'll call those ones O sub D for double. All right, in my single bonded oxygens, there are 6 valence electrons, and it gets to have half of the access to 1 single pair of electrons in the single bond, and it has 1, 2, 3 lone pairs. That makes 6 electrons total. So the single bonded oxygens have a -1 charge. Well, that's about the same as it was before, right? Well, let's see what happens with our double bonded oxygens. All right, 6 valence electrons, and it gets to have access to half of the electrons in the bonds. Since it's a double bond, that number is 4 electrons total now. And as far as lone pairs, there's only 2 lone pairs. That's 4 electrons that are entirely belonging to the double bonded oxygen. So let's do the math. 6 minus 2 minus 4. 6 minus 2 minus 4, 0. And that's where this structure begins to win out. Overall, the formal charge assigned to each individual atom is going to end up being lower than the formal charges assigned to the first structure we drew. But does the charge add up? Let's see. I have a -1 plus a -1 plus 3 zeros, so it's going to add up again to a -2 overall charge. Hey, that works. We decide that the second structure is better because every atom gets to have a lower formal charge on that particular atom than in the first structure that we drew. So that's how we use formal charge to determine the structure that is most reasonable for certain atoms. There's another concept called resonance. Sometimes there's more than one valid structure for a molecule or ion because the formal charges all end up being the same thing. One good example is nitrate. So let's draw some pictures. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons, and there are 3 of them. Then I have a -1 charge, which gives me 1 extra electron to put somewhere. So overall, what do we have? 5 plus 18 is 23, plus 1 more makes 24 electrons total. So I could draw my nitrogen in the middle. Let's put it that way, suppose. And then I'll put my oxygens around it. And I know that nitrogen needs to have an octet. So let me just make a double bond here so that my nitrogen can have an octet. It needs to have 8 valence electrons around it. So now how many have we used up? 2, 4, 6, 8. We have how many more to go? Right, 16. All right, so 2, 4, 6, 8, 10, 12, 14, and there's my 16. Don't forget to put brackets around it to show that the -1 charge of the nitrate ion belongs to the whole entire thing. All right, but wouldn't it be just as good if we drew a structure like this? Nitrogen in the middle, and now this time my double bond is pointing down and to the left instead of straight up. How about that structure? Fill in our lone pairs, and doesn't that look just as good as the first one? The formal charge is going to end up being exactly the same because everything has the same number of lone pairs overall, same number of atoms that have single bonds and double bonds. Or, you know what else we could do? That's not the only way we could show it. What if I drew it this way? Nitrogen in the middle again, single bonded oxygen at the top, and this time let's put a single bonded oxygen in that bottom left and my double bonded oxygen in the bottom right. Doesn't that seem reasonable? Why not? Why couldn't the double bond be down there instead? Again, we put our brackets around to show that that -1 charge belongs to the entire structure. But what's wrong with this? Absolutely nothing. They're all valid, but none of them actually exist because we consider that bond to be delocalized. That double bond is delocalized because it doesn't stay in one place. And it doesn't switch between them either. It is all of those places all at the same time. So really, rather than having a single bond on 2 things and a double bond on 1 thing, we have more like a 1 1/3 bond on all of them, because that multiple bond delocalizes. Now I gotta move some ink. Alright, so we used double arrows to indicate that it is the average of the structures that is most accurate. And remember, the bond doesn't switch between them because it's never really a double bond in any place. The bond is just an average of those. Here's another example of resonance that we're going to save for class time. So here's our basic rules for drawing the Lewis structures. This is what I did. Count the number of valence electrons for each atom and add them up. If the system is charged, we will add 1 for each negative charge on the system, or subtract 1 for each positive charge on the system. Once that's done, we determine the arrangement of the atoms. So the least electronegative atom is usually written first, and it is the central atom. So whatever's written first in your formula, that usually goes in the middle, unless it's a hydrogen atom or a halogen atom. They are always on the periphery because they can only form one bond. They can't be in the middle of anything. They only have the capacity to make one bond. Our next step is to place single bonds between the atoms. So I put my central atom in the middle and then put single bonds between the central atom and all the other atoms. We multiply the number of single steps. We multiply the number of single bonds in step 3 by 2 because each bond has 2 electrons, right? And subtract that number from the number of valence electrons that we determined in step 1. This gives us the number of available electrons to put in all the other places. Then arrange the available electrons in pairs around the peripheral atoms. That means not the one in the middle. We put them around all the peripheral atoms except for hydrogen to fulfill the octet rule for the outside atoms first. Then we arrange any remaining atoms around the central atom so that it has a fulfilled octet. And if all of the atoms, except for hydrogen, have an octet of electrons, then you're done. If it's necessary to complete the central atom octet, you can move electron pairs from the peripheral atoms to form multiple bonds with the central atoms. That means double bonds or triple bonds even if you have to, because if that central atom doesn't have an octet, then we have to start bringing in multiple bonds. Now there are some exceptions to the octet rule that I mentioned in our very first slide. The first one is in molecules that would have odd numbers of electrons, where it's just not possible to complete an octet without an unfavorable distribution of electrons. One example of that is nitrogen monoxide. It has a total number of valence electrons of, for nitrogen, 5, and for the oxygen, 6. There's no way that's going to add up to an even number. So we have 2 possible structures that we can show that get us the closest to fulfilling the octet rule. What do you think? Which one looks better? Nitrogen has only 7 valence electrons, and one of it is unpaired. It's called the free radical. That's this guy. And this structure is actually going to be more stable than this one. Could you figure out why? You could try using formal charge, but truly it's more about electronegativity, right? Oxygen is more electronegative, so it's more likely to have an octet than nitrogen is. Another exception to the octet rule is when you have a very small atom. Atoms like boron, beryllium, and aluminum just sometimes don't have room for a full octet, especially with something that's very, very electronegative. For instance, boron trifluoride. Fluorine has 7 valence electrons, and when there's 3 of them, that's just a lot of electrons crowded in one tiny little place. So here are 2 examples of structures we might sketch for boron trifluoride. You can use the formal charge to decide which one seems like the best bet. You see, boron has an incomplete octet. That's what it's called. An incomplete octet, meaning there's not enough electrons. Look, 2, 4, 6. Only 6 electrons. How about this structure? 1, 2, 4, 6, 8 electrons. Seems like that would be better. But halogens don't get to form double bonds. They only have the capacity to make single bonds, to bond in one place. So you could use formal charge and decide which of these 2 structures is the better, more stable structure. Another kind of exception to the octet rule is when large atoms are surrounded by so many small electronegative atoms that it must have more than an octet around it. And in this case, you would have to have large atoms that are in energy level 3 or higher, because without access to d orbitals, they're not going to be able to do this. They can't exceed the octet unless they have a place for those bonds to go. So some typical atoms that would do this is sulfur, like we saw earlier, phosphorus, xenon, what else? Oh, a few others in that same region on the periodic table. Let's look at phosphorus pentachloride. So the total valence electrons is 42 valence electrons, where normally we might draw phosphorus with this paired electron here, and then the 3 that are unpaired that are spinning all the same direction in the 3p or subshell. Well, let's spread these out to make phosphorus pentachloride. Now I have 5 places where chlorine can come in with its electrons and make some bonds. We got to bring a partner for every electron, right? So chlorine has 7 valence electrons to bring. I use an X to show the one that it's going to share with phosphorus, and then of course the lines indicate a pair of electrons that chlorine is keeping to itself. These are the lone pairs. So chlorine has 7 valence electrons. It's a highly electronegative, and it's a reasonably small atom compared to something, say, like bromine or iodine. So there's our phosphorus pentachloride, where our total number of electrons are 5 for each phosphorus, and then 7 for each chlorine, and there are 5 of them. That's 42 electrons. Crowding that all into an octet just doesn't make sense. And here's a list of some other similar structures for sulfur hexafluoride, silicon hexafluoride, arsenic, xenon, iodine. These are called hypervalent because they have more than what the octet allows for. Now let's look at the term bond order. Basically, we're looking at the number of bonding electron pairs that are shared between atoms less the number of non-bonding electron pairs, and that's going to help us to describe what's called the bond order of an atom. So the number of electron pairs that are being shared between atoms it's a simple math formula: total number of bonds divided by the total number of places to form some bonds. I think we should just give this a try so you see what's going on. The average bond order in the molecule ozone depends on its more stable structure here. So look, I have 1 bond between these 2 oxygens, then I have 2 bonds between these 2. So I add up the total number of bonds. But where do I have places for that bond to occur? Well, not here. This is a lone pair. So I only have 2 bonding sites. So it's 3 divided by 2, which is the decimal 1.5, which is choice 3. And this should make sense. Look, what's the average bond order? I have a single bond here and a double bond there, so 1.5 is like halfway between single and double, right? Well, that is indeed the bond order for the ozone molecule, 1.5. Here's another example. In carbon dioxide, we have 3 different ways we could draw this bond. Maybe a triple bond here and a single bond here, or 2 double bonds, 1 on either side, or a triple bond here and a single bond there. Now you could probably surmise which one makes the most sense, but it doesn't really matter. The bond order is going to be the same. It's a triple bond plus a single bond divided by 2 bonding sites. That bond order is 2. Or in the second example, I have a double bond on either side, 2 plus 2 divided by 2. That's equal to 2. Or in my very last one, I had a triple bond and a single bond and only 2 bonding sites. They all give me a bond order of 2 for the carbon dioxide molecule, because those bonds can be anywhere around there But on average, they still add up to a bond order of 2 because the electrons are zipping around the entire molecule, not just in that one spot. How about the SO bond order in the Lewis structure of sulfur trioxide? So we have 3 different pictures, 3 different resonance structures where it could be. So I have one bond here, a double bond, and a single bond. So 1 plus 2 plus 1. Then I have 3 bonding sites where this could possibly have a bond, right? 3 places where bonds occur. So that is 4 over 3. 4/3 translates to choice number 3, 1.33 in its bond order. So every bond is about 1 1/3. And when we investigate and we actually measure the distance between the bonds, we find that it's greater than the bond length for a single bond, but it is less than the bond length for a double bond. And it should be somewhere in between the two. Okay, the final question for this podcast is how many resonance structures can be drawn for the nitrate ion? Well, I just drew them for you, but why don't you give it a try if you don't remember. How many possible resonance structures can we draw? Remember, nitrate had 1 double bond. Where do you want to put it? At the top? At the bottom? On the other side? Either place where you put it. That gives us 3 resonance structures. Now, some of you clever kids went back and looked in your notes. Earlier in the podcast, we drew these. But just as a reminder, here they are again. There we have bond resonance structures for the nitrate molecule. Well, that's it for now. In our next podcast, we'll look at taking the structures and describing the polarity in the bonds and using the geometry of the molecule to determine whether or not the entire structure will be polar or nonpolar.